I'd like to look at a couple of other examples on proving trig identities. Okay, first of all, I want to prove that 1 minus cosine squared of x all over sine of x plus cosine x sine x equals 1 minus cosine x over sine x. The left-hand side of this particular problem appears more complicated, even though both sides are fractions. On the left-hand side, the numerator, I can think about this in two different ways. The numerator actually reminds me maybe of a Pythagorean identity, if I can make the signs and the numbers work correctly. In the denominator, I see that I actually have a sine function that is common. Let me take care of the denominator first. So in the denominator, I can factor out a sine x, and then that leaves me with 1 plus cosine of x. If I look at what I want to end up with, this will actually help me at this particular kind of problem. The numerator is almost what I need. It's 1 minus cosine squared of x, and I want just 1 minus cosine of x. Okay, well, the square can't just go away, but this that's in the top is actually the difference of squares. And what I mean by that is I mean that that can be factored. In other words, what squares to give me 1? 1 does. What squares to give me cosine? Cosine x does. And then we know in difference of squares, we put a plus sign, we put a minus sign. And so in this particular situation, I wanted to take that numerator and I want to recognize it as a difference of squares, which means I can factor it. So in general, in this problem, I was able to factor both the numerator and the denominator to result in something that could be simplified. From here, I see that I have a 1 plus cosine factor that cancels out in both the top and the bottom, and then I'm left with 1 minus cosine of x over sine of x, and that was my desired result. Okay, this is the first time we've looked at an example as far as factoring trig functions. I'd like to look at one other example where it would involve a factorization of trig functions. Okay, this particular problem, I want to prove the left-hand side is equal to 3 sine of x plus 1. The left-hand side is most obviously the more complicated side. The top, I'm going to notice, is a trinomial. In other words, I have a sine function that's squared. In the middle, I have a sine function by itself, and at the end, I have a constant function. And so what I will do is I will factor that numerator. Okay, the denominator will not factor, so I'm going to leave it as sine x minus 4. In the numerator, I'll need to find two things that multiply to 3 sine squared x. I could use 3 sine of x and sine of x. Then I need two things that would multiply to 4 at the end. I could use 2 and 2. I could also use 4 and 1. Sometimes the term in the bottom gives you a hint. In other words, the term in the bottom is sine of x minus 4. So what I'm going to do is I'm going to try to use the 4 here and the 1 there. Now I need to take care of my signs. The middle term needs to eventually be negative 11 sine of x. Well, if I put my negative with the 4, I can see if I multiply the outer two terms, 3 sine of x times negative 4, that would give me negative 12 sine of x. And then if I add here, that would be plus 1, and that would give me the 11 sine of x I have in the middle. So that's the proper factorization for 3 sine squared x minus 11 sine x minus 4. Okay, this being the case, I see that I have a factor on the top that cancels with the factor on the bottom, and then I'm left with 3 sine of x plus 1. And that was actually the desired result that I was wanting to achieve there on the right-hand side. This concludes my examples of proving trig identities.